nice. So hello everyone. I will try not to stand in the way of the beamer. I'm Alberti from the University of Fribourg, and I'm presenting you today how to improve your workflows, deep learning workflows with DeepDIVA. Right? So I will start to motivate the problem. So we have to first of all admit that we have a reproducibility crisis in deep learning. I mean, we have a lot of new products, but we cannot reproduce them. This is a table that has been presented at the NIPS conference in Montreal last December, and this is just the results of a survey that they conducted on a reinforcement learning paper. As you can see, everyone has experiments because this is the to-go way to show the quality of your product, and almost everyone uses neural network, almost everyone shows you which hyperparameter they used, except if you start going a bit deeper, you don't know what are the parameters for the baseline, which is a bit kind of shady. I don't know how you tune your baseline. I don't know if you're really better than the baseline. And then the further we go down in the table, the worse it gets. The code, open source, it's really nearly half the people. And then how you choose your parameters, it gets worse and worse again, especially when it comes to significant testing. Many people just throw the network one time and then they report the number, and we don't know if it was a lucky run or an unlucky run. And it goes both ways, right? And this is a problem, right? It's a problem in the scientific environment because I cannot verify your results. And now, it's all fun and games, but if you come today and you present me a neural network to do some medical-related task or even financial for that matter, or there are many cases in which you want to trust your network. And if I cannot verify your network or your code, I cannot trust your code. And most importantly, for the scientific, academic point of view, I cannot extend your work, because if I cannot reproduce it, I cannot work on it, I cannot further develop it. And this is a bit against what is the common paradigm in science. When you produce something, you share it with the community, and then we build on top of that, and we go on, right? This is currently not easy to do, right? And then you can say, okay, cool, but you can't implement the stuff yourself. I mean, I explain in my paper how to do it, I don't give you all the secret numbers, but you can try it yourself. Sure, but who has time for that? Let's be honest. You don't have 3 weeks to spend trying to reproduce the work that someone maybe did in 6 months, right? And if you do, it's a lot of overhead, right? And then this leads a bit to this mistrust in a scientific environment, which is not really positive and it's not nice, because then certain results are maybe too good to be true, I cannot trust it, I cannot verify it, and this spirals out of control. And in this moment, we are really witnessing a bit of this, all these issues all together. So there is no magic formula to solve this problem, but what we can do is to start taking steps towards a solution, right? So, two good directions that I present you today is like to ensure at least the reproducibility, and this goes two-way, reproducibility of your own results and of someone else. This is not silly. I mean, I don't know if you ever happened to you, it happened to me already, where you know, you write a paper and then 6 months later someone asks you, hey, by the way, the network that you use, can you share it? And you're like, I have some folder there somewhere, store it, and then you don't find it, you have to rerun it, and you're like out of luck, you have 30,000 scripts and things, and you lose a lot of time to reproduce them, right? Or someone else's, or the problems mentioned before. If I've struggled to reproduce mine, imagine something of someone else, right? And we can promote open sourcing the code. Now, this is of course more academic because industry it's a bit more reluctant to open source stuff for obvious reasons. But even in the academic, there are two major problems for people. When I ask them, hey, would you open source your code? And they're like, you know, it's just this script that I hacked together in a stormy night. It's not really ready to be published, right? I need to refactor it, I need to clean it. And no, if it was good enough to get the job done, it's good enough to share it, right? And the second problem is like code trustworthiness. I mean, do you trust that your code is correct? I mean, especially maybe you have several thousands of lines of code. Is it all correct? Is it bug-free? Sure, you say yes, but really, do you trust it? Do you want me to check it? And not everyone wants to take this risk. There are several cases, especially last year at the ICLR, a paper open sourced the code. Another researcher went into it, found a bug in computing the accuracy. And then when fixed the bug, it was undermining the foundation of the paper. It was basically discrediting everything that the paper built upon because the numbers were not the right one. And you don't want that for your paper, right? So a bit defensively, and we can say wrong, but I mean, it's also hard to blame. People don't disclose their code and fear that someone will point them wrong. And how to contribute to that, we call the framework, DeepDIVA. So we want to help people with something tangible and product, not only good ideas, but something that you can take in your own hands. So we come with a framework which is open source to begin with, otherwise it will be already over, right? And it's built in Python because now it's the to-go language for deep learning related stuff. And it's built on top of PyTorch, which is also an emerging framework. You probably already heard of it. There are TensorFlow and PyTorch. Now PyTorch is kind of taking the lead. It doesn't really matter. The point is it's built on something which is commonly and widespread use. It's not something hidden in our basement in Fribourg. It's something that people use. And it makes your life easier to reproduce your own and other people's experiments, and also makes your life easier with your everyday problems, accuracy computation, plots, and all this kind of stuff, which then it's done by a framework. You trust the accuracy computation because it's done and verified by the community, right? So you are more secure into open sourcing your own code because critical parts are already being taken care of, and you can say, hey, this is not mine, we use the framework, right? It can still be wrong, but at least it has to be wrong for many people. It's safe. So let's start with reproducing your own experiments. This can go two sides, right? It can be on the short term, so something that you did last week, last month, or paper, and you're like, reproduce it. Or it can be something that you published 3 years ago, and it's on another hard drive somewhere else. So the dangers here are mainly kilometers of log files, which are unreadable, and maybe you add a parser that you don't have anymore, and the stochasticity in the process. So we very well know that if you run a network twice, you get two different results. There is even a paper that highlighted that two deep learning solutions, you can make one statistically significantly better than the other if you just choose the random seed accordingly, which is terrifying if we connect it with the fact that only 5% of the paper showed significant tests in the beginning. How we tackle that is not reinventing the wheel, just simple logging management. We log everything in a precise and concise way, and we have different files, and we log literally everything. So there is nothing, oh, I don't remember what I did, because we log all the parameters, all the command line arguments, everything is saved. So you run an experiment, you can take whatever the framework produced and say, with that, you can recreate everything. And then deterministic runs. I mean, this kind of silly, but you need to really check that you're seeing all the resource of randomness in your code. And there are several, and especially this was a bit of an icy one inside the NVIDIA library. You don't really go and think that. You see your PyTorch thing, you see your NumPy random seed, you don't go and think that NVIDIA has a random generator on its own in its library, right? So every randomness is seeded. Then for the long-term reproducibility, the issues are that you might have poor or non-existent use of version control, such as Git. I mean, we had to deal with other things which they had something similar to what is shown in the left, like, you know, project 2, 3, and final, and these kind of things, and it's a mess. And if you think you have to look into that 3 years later, you don't remember which one of the folder you were using, and it's really painful. And then there are hard to dive habits programming. This, I'm also one of contributor for this. You are trying something, you just quickly comment one line out, you try again, you see how it goes, and after 3 hours you don't remember anymore what was commented or not, and the run that you actually use for your plots. And then, this is a bit more nasty, silent data modification, especially now with the cloud, or between coworkers, we have our data stored on the server, in the cloud. And then my coworker comes and modifies the data by binarizing it or normalizing it, I don't know, I don't check, I run again, and I have different results because someone changed it for me. And if you have a million files and only one of them is modified, have fun finding that bug out, right? So we tackle this with Git status. So every time you run something in the DIVA, there is a Git commit which is associated to it. So you run something, it's going to tell you, no, you first commit your code, otherwise you're not going to run, such that when you run something, it's logged. This is what you run. Now, this is obviously a bit annoying if you are developing, so you can turn that off. And to code for that, we copy the entire code base every time you run something, just the code, so it's just a few kilobytes, it doesn't produce anything huge. But at the very least, when you run something and you have your output folder, in there is the exact code that generated the results. So if you commented something out and you don't remember what, well, you just go and check. This is what you commented out. And then we have data integrity management. So what we do is we go through your data, we hash every single file of it, and we store the hashes of all the file in a JSON in a relatively smart and simple way, such that when you run again your data, you can verify, is it the very same data that you ran back then? If yes, cool. If not, I tell you, hey, this file is different, and you don't lose time. First of all, you know that something is different, and you know which file is different with the hash, so you can rename them, and it's not going to matter. Now, this is cool if it's your code. But what if I tell you to reproduce my experiments? What will you need to do that? Well, you only need the Git repository where I put my code, because it has to be open source, we said in the beginning, and I tell you exactly which commit, otherwise it's also a bit lost. And then the list of common arguments you used, when you have it, because the framework saves it for you, so you just take this file with the command line arguments, you tell me this is the commit, and if applicable, you give me the data. If it's your own data, you have to give it to me. If it's ImageNet, it's publicly available, I can just take it myself. But with these 3 components or 4, you can reproduce the experiments and have the very same exact number. Now, this is how you ensure that the reproducibility is there. Now, what can the framework do on top of that? I mean, this is fancy logging, fine, but why is it useful? It's useful because we call it the one-click-away deep learning scenarios. Because every time that we get a new project, you start and it's like, okay, but this is like similar to what we did last September or whatever. And we have this 8 starting point. It's just because this is what we worked on, but you have several ones. You can see we have image classification. It's a traditional one, or image similarity, which is also the Google reverse image. You give an image and you want to retrieve similar ones, or you want to recognize action into a video, semantic segmentation. I mean, there are several ones. It's unimportant. What it matters is that you have a new task, a new project, and you say, okay, what does my task look like? Is it like one of these? If yes, you're going to copy-paste the code that runs this and modify only the relevant part. If you want to do some fancy classification, you start from this code and you just modify the parts that suits you. So that everything else, it's still good. The accuracy, you don't touch it. The plots are still all the same plot. I mean, a lot of the code, if you work with deep learning, it's always the same story all over again. Data loader, feed it into the network, run it through the network, measure statistics afterwards, produce plots and log. A lot of boilerplate code. And this is already there. And these are at least diverse scenarios. You just take the most similar for you, you fork from it, and you're good to go. You only need to modify the relevant parts. This is a common saying in machine learning. We say, like, when the data is ready, the task is solved. If you ever had to prepare a data set yourself, you know what are the steps to go through, and it's really time-consuming and tiresome to just prepare the data, have it on the hard drive such that you can throw it into a network. This is uneasy most of the times. With DeepDIVA, we have several scripts which provide you with the most common data set. ImageNet, Cypher, there are some medical images, historicals, there are several ones. So if you just quickly want to try something out, a click, you get your data, it's ready, you run, good. And you did not waste time, hours formatting the data in the right format and whatnot, right? And then splitting the data set, this is a critical step. You need to do it properly. You need to split your test set, taking care of the class distribution and a lot of pitfalls. If you every time have to do it yourself, you just lose time. It's nothing super fancy, but it's something that comes out of the box. It's nice to have. And then analyzing the data. This is something critical for neural networks. Normalizing the data for mean and standard deviation, or knowing your class distribution, this also comes out of the box from the tool. And the data integrity is what I talked about before with the JSON and the hash. We just make sure that the data you are running to is the data you expect it to be running on. So this is just a sample. I couldn't put them all of visualization that comes already out of the box. We leverage, again, we didn't really reinvent the wheel in our framework because this is exactly the foundation of the idea. We use TensorBoard, which comes from TensorFlow, developed by Google. It's just a website you can host on your server. Then you can look at your results in real time. So as your network trains, you can already look what is happening, what is the score, what is going on in your network. And the kind of visualization you can have is several plots of whatever metrics you want to come up with, whether it's accuracy or loss or whatever, and then some images that comes out of it. Confusion metrics tells you, in the case of classification, what is your distribution of the outputs. You can look at the weights of the network, visualize the features using TSNE, so you can see how does the feature of your network look like when it's being learned. And finally plots, where here you have enforced that in this example I run it 10 times, automatically the framework says, okay, you want to run that, it runs it 10 times in a row, and it tells you the max, the mean, the average, the standard distribution, all kind of metrics that then you can come into your paper and say, I'm sure because they run it 10 times, and then significantly better than the baseline, right? And you don't have to bother it coming there. Finally, the story of the hyperparameter optimization. There is a lot of research going on how to do it, how to not to do it. Again, with the philosophy of not implementing the wheel, we used a third-party software. This is SIGOPT, is a company, but it's free for academics. And so in our scenario, we are academics, it works. And this software basically just ignores entirely what you are doing. It just takes your output and tells you, okay, given these parameters, you score that, and it tries to predict what are the good hyperparameters for you. And they don't do it with black magic, but they do Bayesian optimization for finding them. This is way faster and way more reliable than doing the random search or grid search. You will never see the end of it in certain times. So there are many solutions like that. We picked this because it was convenient and free, but there are many. But this is already integrated, so you don't have, again, to lose time trying to find your own one and then, right? It's all the same story. And then wrapping it up, how to use it. I mean, good story, but in the end, how do you use it? Well, from the website, you can set it up on your machine from no time, because there is a script which sets it up for you, so you don't have to bother. You run the script, it prepares you the Conda environment that it then will run the framework. If you don't know what Conda is, or you don't know if your machine is running it, you can use Docker images, which nowadays are really common to deploy it, especially on the cloud or whatever remote machine you have. We have a documentation, which to the best of our thing explains a bit how things are working, and it's very useful if you get into the code base of someone else that at least is documented. And then we have tutorials, because at least the most common scenarios we covered with a short tutorial. Look, this works like this, and then you don't have to waste hours, because it will also not be the point. We want the people to use the framework, we want also to help them learn how to use the framework in the first place. And again, the idea is that you fork it and then modify what you need, if at all. Certain solutions are already 100% there, ready to ship. You just put your data, choose your model, and it runs. If you have some special things, you just modify these special parts. And that will be it for today. Here you can find the framework webpage, where you find, again, everything that I say, the tutorial, the documentation, and the link to the GitHub repo, if you want to try it out. And that will be it for today.